Do you have problems tonight that you want to verbalize, or do you want to take a picture of something and send it to me by email, or are you getting problems off the internet and can I go to that site directly?
Let's see. I think I can share with you.
I'm sorry, what?
I think I can share with you the book that I'm using.
You can verbalize it?
Well, no, I think I can send it to you.
Okay. You want to take a picture with your cell phone and send it to me?
I think I can send it over the computer, actually. It's a
Okay.
PDF. So
You can, I don't know if you can
maybe
send a file or not.
I'll just try and send the link.
Okay, that'll work.
Chat.
Yeah. I got a error.
Let's see. Maybe I'll
Try that again. Yeah, I don't. It doesn't like that.
Okay.
You might have to. Can you email me the PDF file?
Yeah, I'll do that.
Okay, you have my email address?
No.
Let me write it on the screen here.
Okay.
And then probably you want to save it so that in the future you can send pictures easily.
Okay.
David Cowan 1949 at gmail.com.
Let's see.
I'm going to close out my camera here just because whenever it's not like me to run very much.
Okay. I sent it.
Okay. Might take a few seconds for me to get it, or half a minute. Yeah, there it is. Okay.
So tonight I have to do. Let's see. Let me just pull up the homework here. I tried looking at them and I was kind of confused, so I saved them for this. I have to do page 50 to 52, so scroll down a little bit. And 4 through 8, 10, 11, 12, and 15. So.
Okay. 50 through 52?
Yeah.
Okay. So here's 50. Number 4. Okay. Complete the sentence. Question mark is written in terms of question mark for the given formula. So area is written in terms of the side length, or A is written in terms of S.
Okay.
Number 4.
Yeah, I think that's what I had.
And maybe they want area is written in terms of the side length of the square. I don't know what your teacher's looking for there.
Okay.
Number 5, the volume is written in terms of the base and the height.
So base plus height or something, or?
Well, it's written in terms of base times height.
Okay.
I hate these problems about terminology because everybody's terminology tends to be a little different. I don't know exactly what they're looking for. As long as you know that volume is 1/3 of the base times the height for a pyramid, that's what's important. Or the area of a square is the side length squared. So maybe they want areas written in terms of S squared. I don't know.
Okay. I'm sure base times height is all right.
Do they have an example so that we can see what they are looking for here? All right. Okay, so if we look at number 6, right?
Yeah.
Just go through each of these.
Yeah.
Okay, let me go back and look at example 2.
This one I was pretty confused about. I didn't really understand what it was asking.
Okay.
I mean, I understood, but I didn't really understand how to get an answer from it.
Okay, they've made it easy for us. They've given us a formula that allows us to compute the number of hours needed for one car to catch up with another car if the first car is going at T, has been going for T hours, driving at 65, and we can solve for C by plugging in. So if we assume the first car has a 2-hour head start over the second one, we're trying to find out its catch-up time, which is C. What is R again? R is for one car driving R miles per hour to catch up to another car that is T hours ahead and driving at 65. Well, obviously, if R was 65, we would never catch up, right?
Right.
So R has to be greater. And notice also that if R is 65, we're going to be dividing by 0, which violates the first rule of mathematics. So this is just going to be algebra. So the first car has a 2-hour head start, then T is 2, right?
Yeah. That's what I wrote down.
Okay, so here, let me bring up my, in fact, let me do a few things here. Let me close out my, that so it doesn't interfere with anything. And then let's begin on this here. So my formula is C equals 65T over R minus 65. They want to know C for various speeds. So in the first case, I know T is 2. It had a 2-hour head start.
Yep.
And I'm going to plug in 75 for R. So if you're going 75 miles an hour, it's going to take you 13 hours to catch up. See that?
Yeah.
Okay, if we're going 85 miles an hour, it's 130 divided by 20, which is only 6.5 hours. And if I'm going 45 miles an hour, how long is it going to take?
So it would be C equals 65 times 2. Um, 130 over -20.
Okay, what's that mean in a real life context? a negative number.
I mean, I guess it would mean that he's never going to catch up.
And he shouldn't. If he's only going 45 miles an hour and the other car is going 65, he is not ever going to catch up.
Okay.
Okay? Okay. Now number 7 says solve the equation for R. So let's manipulate this and isolate R on one side and everything else on the other. So what's our first step? We've got 3 variables. We got a C, we got a T, and we got an R.
Yeah. So what is the C? C is the C is just the
catch-up time, but it's just a variable. In other words, to do number 7, they want us to solve this equation, this formula for R.
Right.
So let's do that.
Okay.
So what's the first step in solving for R?
I always get kind of confused with these. I know it's kind of like...
Usually when there is a denominator in an equation, the first thing you want to do is get rid of it.
Okay.
So how do I get rid of the R minus 65 that's in the denominator? How about I multiply both sides by R minus 65?
Okay, yeah.
Okay, what's that give me on the left side? Now distribute that C.
So RC minus 65C
equals
equals 65T.
That's it, because that canceled with that.
Oh, right, yeah, yeah.
Okay, so we're trying to solve for R. So we only have one term that has R in it. So we want to make everything else over to the other side. So what's the next step?
So I guess we would combine the C's.
Can't do that.
Oh, we can't?
We're trying to solve for R, so we want to isolate this.
Right, but wouldn't we take the C minus 65C, so it would be...
I want to move it to the other side. So I want to add 65C to both sides. So now I've got RC equals 65T plus 65C. And now one last step. It's almost always the final step of solving an equation. Divide by the coefficient of R, which is C.
Right.
So R ends up being 65T plus 65C divided by C. So that's the equation solved for R.
Okay.
No matter how complicated an equation is, you can always solve for one variable. Well, I take that back. There are very complicated ones that are hard to solve for a variable, but usually they're cubic equations or higher. As long as it's a quadratic or less, in other words, this is linear, then you can always solve for the variable. All right. Let's look at, whoops, I probably shouldn't have erased that, because I bet the next question, okay. Notice what well, let's read the question. Imagine you're riding in the second car in a situation of example 2. Let T be the number of hours ahead. Start, the other car had a speed of 65. Let C be what it is, and R be what it is. So in time C, you will have traveled RC miles, while the other car will have traveled 65 times the head start it had plus C miles. Thus, you catch up when RC miles is the same as 65 times T plus C. Well, notice this was halfway through our solution. We had this. When we solved that for R, one of the steps we had, the second to last step we had was this.
So we just we can divide it by R, right? Or
Well, if we're solving it for C, well, there's a problem here. If I'm solving this for C, I want to gather all the terms that have C in it on the same side.
oh, right.
I can't just divide by R and get this, because that's not really what C is. You can't have C being equal to something that still has C on the other side.
Right. They have to be on
When
the
you're
same
solving for C, you want no C's on the other side. So in this case, we have to do a little different. We have to bring this term back over to there. So we make it RC minus 65C equals 65T. Now it's a factoring problem. If we want to solve for C, we factor it out. What's left behind when I factor out a C?
Just 65?
No. We're going to divide C into both terms, so I'm left with R there minus 65.
Oh, right.
Notice that when I put these two back together again, I get what I started with.
Okay.
That's equal to 65T. Now we can solve for C by dividing both sides by R minus 65. So C equals 65T divided by R minus 65, which is what we started with in the first place.
Right.
So we solved for C.
So C equals 65T divided by R minus 65.
Which is what we started with. If you look at number 6 or example 2, that's what they gave us to begin with.
Okay.
So all we did was we manipulated this to solve for R, and then we manipulated it again to get back to C.
Okay. Yeah, I understand that.
They've really gone out of their way to make this confusing.
Yeah.
But as a pure algebra problem, it is not confusing at all. In other words, they've made it confusing by putting it into the context of an applied mathematics problem,
Right.
which I understand why they want to do that, but what they're really trying to teach you here is the algebraic manipulation of these two formulas, how to solve for R and then how to solve for C if you've already solved for R. Okay, so if we look at number 9, which formula is
skip number 9, go to 10.
Okay. In chemistry, a given mass and volume will satisfy this equation. Okay. Which is an equivalent formula solved for P sub 2. So let's start with what they gave us. T sub 1 over P sub 1 equals T sub 2 over P sub 2. So let's solve this one for P sub 2. So what's the first step?
Okay. So the first step to solve for P.
Well, remember the first step is usually to try to get rid of your denominators.
Right, so times by, well,
When you have two denominators like this,
yeah.
there's a method they say cross-multiply.
Oh, yeah.
Cross-multiplying is really just two steps in one. In other words, what I'm really going to do is I'm going to multiply both sides by P sub 1, and then I'm going to multiply both sides by P sub 2. So those two steps done in one step give you this. T sub 1, P sub 2 equals T sub 2, P sub 1. You see how I got that by cross-multiplying?
Yeah.
Multiply that, multiply that. Now solve this one for P sub 2.
So in this one we would just divide by T1 on both sides.
There's a piece of 2, which agrees with D. In other words, you can switch the order of these, obviously. The associative property holds.
All right, awesome.
Okay.
Next one is 11. Yeah, 11 and 12.
Okay. They give us a picture. So the pitch on this would be the ratio of the vertical rise, which is the amount from the vertex to the base, divided by half of the span. Okay, so let's write the formula first. P is equal to R over 0.5 S, and solve the pitch formula for S. So first of all, let's manipulate this equation to solve for S.
Times by 0.5 on both sides.
Okay, so we got 0.5 times by 0.5 S, gets rid of that denominator.
Oh, yeah.
Now I've got to divide everything by 0.5 P. So S, since that cancels and that cancels, S is equal to R over 0.5 P. So S equals R over 0.5 P. And in part B, if a builder wants a roof to have a pitch of 6/5 and a rise of 8, what's the span? So how are we going to do that?
What's the span?
In other words, we have the formula to solve for span. S is span.
Right.
So we need to plug in R and P.
So, right. So it would be S equals 8 over 6/15 P.
And P is 6/15. So it's actually 0.5 times 6/15.
Oh, okay.
Right? In other words, there's the 0.5, and the P is 6/15.
Okay.
So that's what S is. Now we have to simplify that. We can do this a couple of ways. We can multiply the 0.5 times the 6 and get 3/15 as our first step. And then how do we divide 8 by the fraction 3/15? Flip the denominator and multiply. In other words, we don't know how to divide by fractions, but we know how to multiply by fractions. So you take every division problem and you turn it into a multiplication problem. So 8 divided by 3/15 is the same as 8 multiplied by 15/3. Okay, well 15/3 is 5, so 40 is the answer.
All right.
Now, did you see how I got 3/15 out of 0.5 times 6/15? I multiplied the numerators. 0.5 times 6 is 3.
Okay.
Okay. Okay, so we need to do 12 next?
Yes.
Okay, so a photographer shows the roof of that using the interior triangle, measure the rise and span of the roof, and estimate its pitch. Okay. We know the rise is 8. The span was 40. I'm assuming that that's what they mean by span. So they want to estimate this pitch right here based on this triangle.
Okay.
And the pitch is going to be the length, I guess. The measure of the steepness. So actually the pitch is going to end up being the slope of that roof.
Okay.
Well, the slope of that roof is a rise of 8 over a run of 20. So the pitch is 4/10 or 2/5. Now, let's go back and just to make sure that I'm understanding my terminology right here, is the pitch 2/5? Well, the rise is 8, half the span, yeah, half of 40 is 20, 8/20 is the same as 2/5. So the pitch is 2/5. But notice the pitch is the slope of that line, and the slope of that line is rise over run. 8
Right.
divided by 20.
Okay.
This is from online textbook?
Actually it's not, but the one of the teachers is scanning it slowly, so
Oh, okay.
hopefully they'll continue to do that.
Okay. All right. And next one
And
is 13?
15.
15.
15.
Okay.
Yeah.
Okay, that's the formula for the area of a trapezoid with its two bases. You know, a trapezoid is defined as a quadrilateral that has exactly two opposite sides that are parallel. So that's what makes a trapezoid, and those opposite sides are base 1 and base 2. So it's kind of like the area of a rectangle is base times height, only with a trapezoid it's the average base. Well, what's the average base? It's base 1 plus base 2 divided by 2. So that's how this formula is arrived at. It's similar to the area of a rectangle. Only a rectangle has the same base 1 as base 2, and a trapezoid has different. But the height they are referring to is the vertical height. Okay, so this being algebra, not geometry, they want to solve this formula for B1. Okay, what am I going to do? How do I algebraically manipulate this so that I end up with B1 equals something over here that has H, A, and B2 in it?
Right.
What's the first step?
I don't know. This one's hard. I'm not.
Let's get rid of that denominator. There's a 2 over here.
Oh, yeah.
Okay, well that's easy enough to get rid of. Now what? What can we do with this H times B1 plus B2? distribute it.
Yeah, distribute.
Distribute it, which gives me this.
HB.
Now our goal, since we're trying to solve for B1, is we want to isolate. That's the only term that has a B1 in it.
Right.
So we want to get this on one side of the equation and everything else on the other. So what's the next step?
So the next step is to minus HB2 from each side.
So that gives us this. And it leaves this on the right side. Now the final step, which is almost always the final step in solving an equation.
Divide by H.
Right. So now we have B1 as a function of area, B2, and H.
All right, yeah.
Again, probably a little more sophisticated algebra than you came across in Algebra 1, but there's really not much difference between Algebra 1 and Algebra 2. It's just more of the same.
Right.
And they're throwing in geometry formulas. I'm not sure why. I guess. Okay, so 16?
No, that's it for my homework.
Okay. You want to go over any of the methods for solving equations? Complicated equations. Like 17 has some complicated equations. Do you know how to solve all three of these?
Let's see. Yeah, let's go ahead and do that.
Okay. The first one's easy enough. What's the only step I need to do to solve for x?
Divide by 5/8.
That's correct. If I divide both sides by 5/8, but what's that the same as? Multiplying by what?
By 8?
By the reciprocal. In other words, if I multiply by 8/5, everything cancels and I'm left with x, which is what I want. So now I have to multiply this side by 8/5. Same as dividing by 5/8. Okay, now I get x equals, well, I can do this, 16.
Okay, so...
Okay, B is more the same. C is a little different. Let's look at C. C, we have 5/8 x plus 30 equals 10 plus 1/3 x. What am I going to do here?
Let's see. So we want to get the x's on the same side.
Right. We want to gather together like terms. So anything with an x in it wants to be on the left side. Everything without an x in it needs to be on the right side.
Well, we could do the divide by 3 or the reciprocal.
Not yet, because we don't have a division yet. In other words, to get the x's all on one side, I need to move this over to here. And to get the numbers all on the one side, I need to move that over to there.
Okay.
So I can do that. I can do 5/8 x minus 1/3 x equals 10 minus 30. Now, how do I do this?
Would we find a common denominator?
Correct. Which is? Hi, get down. Get off that table.
24.
Okay, so 24 is going to be my common denominator. What's this term up here going to be?
that's going to be 5x.
In order to get 24 as a common denominator, I have to multiply this fraction by 3 over 3.
Right.
You can always multiply a fraction by 1 without changing its value. So this has to be 15x. In other words, 15x over 24 is the same as 5x over 8.
Right.
So what's this term going to be?
That will be 8x.
Okay. Now I've got this. I can simplify that because now I can operate on the numerator. So I got 7x, which is 15x minus 8x, over 24 equals negative 20. What's my next step?
Hold on, I'm just writing down some notes.
Okay.
Okay, so the next step would be to times by 24.
Okay, so we got 7x equals minus 480. Now what?
Now we would divide by 7.
Right. So there's the answer. It can probably be simplified. 4 goes into that. 7 goes into that. It's going to be an odd number. So whether you want to turn that into a proper fraction or an improper fraction is up to you. That's a perfectly fine answer.
All right.
Okay. Now, we could have done something a little different as our first step. We could have found our common denominator and multiplied every term by 24. And that would have gotten rid of, notice what happens if we do that. In other words, when you're solving equations, there's always multiple ways to go. Kind of what I like to do is to get rid of the denominators always as the first step. Well, if I got rid of the denominators instead of combining like variables first, I can see that my common denominator is 24, so I'm going to multiply both sides by 24. Well, when I multiply this term by 24, I get 15x. When I multiply this by 24, I get 720. Multiply 10 by 24, I get 240 plus 8x. Now it's a much easier equation to deal with because there's no fractions, no denominators.
Okay.
I'm still going to move the 8x over there, leaving 7x. I'm going to move the 720 over there, leaving minus 480. I'm going to get to exactly the same spot. It's just, to me, it's half dozen of one, six of the other, as long as you're aware of both techniques.
Okay.
There's nothing wrong with doing it the way you did it. It just involves fractions more.
Okay.
Okay. Is there anything else you'd like to go over?
Let me see. I know we have a test coming up, so I'm going to look at my notes.
Okay. You can verbalize some of these problems to me if you want. It's not like I have to be reading this. You can just read them out loud.
Okay. Well, let's see. I don't really have any specific problems, but we've been doing a lot with functions and
Domain and range? Have you gotten a domain and range yet?
Yeah, a little bit. We could go over those.
Okay, let's talk about domain and range. If I tell you that this is a function, and it doesn't matter if I say y equals x plus 1 or if I say f of x equals x plus 1. Y and f of x are usually interchangeable.
Okay.
Okay, if I'm going to graph it, I can call this the x-axis and call this either the y-axis or the f of x-axis. Well, if I put this in y equals mx plus b format, I know that y-intercept is 1, has a slope of 1. It's going to look like this. When I'm talking domain of this function, I'm talking about what are all of the allowable values for x. Well, we can see that I can make x anything. I could make x a billion, I could make it minus 10 billion, I could make it a half, I could make it minus a half, I could make it 0. There is no restriction on x. So the domain of this function is all real numbers. I draw the number line, goes from negative infinity to positive infinity. Any point on that number line can be used in this function.
Okay.
Range is what are all the possible values for f of x or y. And you can see that that can go from negative infinity to positive infinity also. So for a function that's as simple as this, the domain is all real numbers and the range is all real numbers.
Okay.
But let's make it a little different. Let's make it y equals square root of x. Now, what are all the possible values of x? Can x be negative?
No.
No, because you can't take the square root of a negative number. Can x be 0?
No.
Yeah, actually it can be. You can take the square root of 0. The square root of 0 is 0. So if I'm talking domain for this function, then whatever inside the radical sign has to be greater than or equal to 0. So I would say x has to be greater than or equal to 0. There's your domain. What's the range? What can y be? Well, y can never be negative either, because when you take the square root of a number, you always get a positive answer. So the range would be y is greater than or equal to 0. Okay?
Okay.
Let's take another function. What's the domain there?
So this one.
When you're thinking domain, always be thinking what can x not be, as opposed to what can x be. It's easier to figure out what it can't be. Can x be minus a billion? Yes.
Yes.
Can x be plus a billion?
Yes.
Can x be 0?
Yes.
No. First commandment of mathematics is thou shalt never, ever divide by 0.
Okay.
So x cannot be 0. So here the domain would be x is all reals except x cannot ever be 0. Well, what's the range of this function? Is there any number that y can't be?
No. Y can be any number.
Actually, it can't be 0 because the numerator is a number. The only way y can ever be 0 is if the numerator is 0. Notice that no matter what value you plug in for x, you cannot make y equal to 0. But y can be any other number. If I wanted y to be 1,000,000, then I'd make x 0.00000001. Now y would be 1,000,000. If I wanted y to be minus 1,000,000, I make it minus 0.000001. So I can make y virtually any number that I want except 0.
Okay.
So the range is the same here. It's all reals except y can't be 0.
Okay.
That's pretty much the way you handle domain and range.
Yeah, that's...
And I'll give you one more just to lock it in here. What's the domain of this function?
So y equals 1.
No, if we're talking domain, we're talking what can x be? What's the first requirement that x has to be?
X has to be larger than 2?
Yes. Normally, if I would have said this, the domain of this function, I take whatever's inside the radical and I say x minus 2 has to be greater than or equal to 0, which means x has to be greater than or equal to 2. But I've complicated it a little bit by making it in the denominator. So x has to not only be greater than or equal to 2, but can it be equal to 2?
No.
Because then I'd be dividing by 0. So the domain for this is actually x has to be greater than 2, whereas the domain for this would be x is greater than or equal to 2.
Okay.
So it depends on the context of the function. But basically the restrictions you're always looking at is you can only take the square root of 0 or positive numbers, and you must always divide by something other than 0. Those two things will always allow you to figure out domains at this level. Once you get into logarithms, then there's further domain restrictions. If I said the following, have you had logs at all in Algebra 1?
No, I know we're going to have them, though, this year.
Okay. Well, if I said this function, what can x be? Well, we can only take logs of positive numbers. We can't take the logs of negative numbers, and we also can't take the log of 0. So this domain is actually more restricted than this one. In this domain, I can let x be 0. In this one, I can't even let x be 0. So here, x would have to be greater than 0. Here, x would have to be greater than or equal to 0. It's a subtle distinction, but a very important one.
Okay.
When you're dealing with domains and ranges, because if you answer a question this way instead of this way, you'll lose points on it. For sure.
All right.
Because they're different answers. Okay, so domains are easy. Ranges tend to be what's hard. Ranges require a little bit more out-of-the-box kind of thinking.
We've also been doing a lot of problems that are like, let me see, rate times time equals distance. And
okay, this is a very key formula for you, not just in algebra, but when it comes time to take the SAT or the ACT. You want to memorize this and always memorize it as that. Don't memorize its manipulations. In other words, this means also that rate is equal to distance divided by time. It also means that time is distance divided by rate. So there's all of these that you could memorize, but that's just going to make it confusing. I'm a firm believer that you want to memorize one formula only, and then any manipulations that you need to do, you can always do. But memorize it as this.
okay.
If I want to drive to Colorado Springs, which is a distance of 60 miles, and I want to do it in 1 hour, then the rate I have to go is 60 miles an hour. In other words, this is 1 hour, so I'm going to divide both sides by 1 hour. and I get rate is 60 miles per hour. Do you have a specific distance, rate, time problem you want to look at?
Not really. The distance equals rate times time is a little bit more simple to understand, but we've been doing some where it's like you want to buy a pound of nuts to add to your candy bag, and they're $5.06 or something like that.
Okay.
You have to have, and your candy bag has to equal like 7 pounds. You know, I mean, they're similar, but they're just different.
So they're word problems, what you're talking about. Okay, word problems give a lot of people a lot of trouble, but if you approach them all exactly the same, I guarantee I can show you how to do any word problem you're going to come across.
Okay.
So we need a word problem to let me explain that to you, though.
Let me get one.
See if you can find a simple word problem.
Okay, here's the one that I had some trouble with. It's the same one with the candy.
Okay.
So I decide to buy trail mix.
Okay.
At Whole Foods containing a mix of nuts and chocolate.
Okay.
The chocolate costs $6.97 per pound, and the nuts cost $5.65 per pound.
Okay.
If I buy a total of 15 pounds and pay $90.69, how many pounds of chocolate and how many pounds of nuts did I buy?
You bought a total of 15 pounds.
For $90.69.
Okay. So the first thing you want to do for a word problem is define your variables. What are they asking? How much chocolate and how much nuts? So we're going to let X be the amount of chocolate, and we're going to let Y be the amount of nuts. Always the first step. If you start every word problem with defining your variables and actually spell them out until you get so comfortable with them you don't have to spell it all out. Okay? Yeah. So now I can write an equation. I know that I bought X amount of chocolate times $6.97 a pound. That'll give me my price of my chocolate, plus I bought Y amount of nuts. They are at $5.65 a pound, and I know I spent $90.69. So there's one formula with two variables in it. I can't solve that. I need another equation. Well, what's my other equation? What is it?
It's
X plus Y equals 15.
Oh.
Right? You see why?
Yeah.
Okay. Because you were told that you bought 15 total pounds, so I know that the X plus the Y has to equal 15. So X plus Y equals 15. There's my second equation. I have two equations, two unknowns. I can solve that. Do you know how to solve two equations and two unknowns? You can do it by substitution or elimination.
Okay.
But that is a perfect word problem to show you exactly how to solve word problems. Now,
Okay.
there's another way I can do it. Let me just point it out before I leave.
I don't get how I would solve this, though.
Well, okay, let's solve it by substitution. I'm going to solve for y. What is y equal to? 15 minus x. Now I'm going to go back into this equation and substitute 15 minus x wherever I see y.
Okay, hold on.
So now I have 6.97x plus 15 minus x times 5.65 equals 90.69. Now notice I have one equation and one variable.
Okay.
Okay, you know how to solve this?
Yeah, let me just write it down.
Okay, I don't want to waste time going through this if you know how to do it, but there's one other step I do want to point out here. We do not have to use two variables here. When I defined my variables, I said x was the number of pounds of chocolate and y is the number of pounds of nuts, but I really could have stayed in one variable by saying, let's let x be the amount of chocolate and 15 minus x be the amount of nuts, because I know that's true, right?
Mm-hmm.
So now, by staying in one variable, this is a bit of a leap that you have to learn to kind of make. It's not obvious that the amount of nuts would be 15 minus x, but it's true. If x is the number of pounds of chocolate, then 15 minus x has to be the number of pounds of nuts. So now I can immediately write my equation 6.97x plus, well, the amount of nuts is 15 minus x times 5.65. In other words, I don't really need to introduce a second variable. It just makes it a little easier to understand, I think, by using two variables instead of one. One thing that you have to know that if you're going to use two variables, you need two equations to solve it. If you give me one equation and two variables, I cannot solve it. There's an infinite number of solutions. So if I have two variables and I want to solve for both of them, I need two equations, or I need to set the problem up so that I only have one variable.
Okay.
Okay? That's probably a good place to stop for tonight.
Yeah.
Hopefully that will clear up word problems. But just remember, word problems define your variables, and you define your variables by looking at the final sentence of the word problem on what they're asking for. In other words, the final sentence of that word problem was how much chocolate and how much nuts. So we go immediately, we know how to define our variables. They're looking for two things. Let's let x be chocolate, y be nuts. All right. You want to just continue to schedule online as needed, or are you looking for a regular weekly session at a certain time?
I mean, I'm planning on doing it weekly, but I think I'll just schedule